Hello everyone. In this lecture I will talk about transfer and transport of municipal solid waste. Let me try to give you some introductory information about transfer and transport operation. In the field of solid waste management, the functional element of transfer and transport refers to the means and facilities used to effect the transfer of waste from one location to another, usually more distant location. Typically, the contents of relatively small collection vehicles are transferred to larger vehicles that are used to transport the waste over extended distances, either to material recovery facilities or to disposal sites. In the slide, you see a flow diagram showing the elements of integrated solid waste management system. As you see here, the transfer and transport operations are between the collection and final disposal steps. Transfer and transport operations are also used in conjunction with material recovery facilities to transport recovered materials to markets or waste-to-energy facilities and to transport residual materials to landfills. Today, with rising labor, operating and fuel costs, and the absence of nearby solid waste disposal sites, transfer stations are becoming common. Now let's try to find the answer of the question, why do we need for transfer operations? Transfer and transport operations become a necessity when haul distances to available processing centers or disposal sites increase, so that direct hauling is no longer economically feasible. They also become a necessity when processing centers or disposal sites are sited in remote locations and cannot be reached directly by highway. Now let me tell you some of the factors that tend to make the use of transfer operations attractive. Occurrence of illegal dumping due to excessive haul distances, location of disposal sites relatively far from collection routes, use of small capacity collection vehicles, existence of low-density residential service areas, use of a hauled container system with relatively small containers for collection of waste from commercial sources, and use of hydraulic or pneumatic collection systems. Transfer stations are used to accomplish transfer of solid waste from collection and other small vehicles to larger transport equipment. Depending on the method used to load the transport vehicles, transfer stations may be classified into three general types. The first type is direct load, the second one is storage load, and the last one is the combined direct load and discharge load. In the slide, you can see the schematics of the three types of transfer stations. Let me first talk about the direct load transfer stations. At direct load transfer stations, the waste in the collection vehicles are emptied directly into the vehicle to be used to transport them to a place of final disposition or into facilities to compact the waste into transport vehicles or into waste bales that are transported to the final disposal site. In some cases, the waste may be emptied onto an unloading platform and then pushed into the transfer vehicles after recyclable materials have been removed. The volume of waste that can be stored temporarily on the unloading platform is often defined as the surge capacity or the emergency storage capacity of the station. In the storage load transfer station, waste are emptied directly into a storage pit from which they are loaded into transport vehicles by various types of auxiliary equipment. The difference between a direct load and a storage load transfer station is that the latter is designed with a capacity to store waste, typically 1 to 3 days. In some transfer stations, both direct load and discharge load methods are used. Usually, these are multi-purpose facilities that service a broader range of users than a single-purpose facility. A multi-purpose transfer station can also house a materials recovery operation. In a large capacity direct load transfer station, the wastes in the collection vehicles usually are emptied directly into the transport vehicle. To accomplish this, these transfer stations usually are constructed in a two-level arrangement. The unloading dock or platform from which the waste from collection vehicles are discharged into the transport trailers can be elevated, or the transport trailers can be located in a depressed ramp. In the slide, you see the photographs of 3 different direct load transfer stations without compaction. In these stations, the waste in the collection vehicles are emptied directly into the transport vehicle. In the first and second photographs, you see transfer stations constructed in a two-level arrangement. The unloading platform from which waste from collection vehicles are discharged into the transport vehicle is elevated. In the transfer station in the third photograph, a special equipment is used to directly load the waste from the collection vehicle to the transport trailer. In this way, both the collection vehicle and transport trailer are at the same level. A small capacity direct load transfer station with compaction facilities is shown in the slide. As shown, a large container is used with this type of transfer station as opposed to a transfer trailer. The container is hauled to the disposal site using a tilt frame vehicle. Depending on the length of time required to haul the loaded container to the disposal site and to return, an empty container may be attached to the compactor before the full container is hauled to the disposal site. In the slide, you can see an example of large capacity direct load transfer stations with compactors. The compaction facilities can be used to compact waste directly into the transfer trailers. The operation of a direct load transfer station with compaction facilities is essentially the same as the operation of a direct load transfer station with open trailers, except that the waste are compacted into large transfer trailers using stationary compactors. In some cases, the waste are conveyed to the compaction facilities. In the transfer station shown in the slide, the waste are first discharged into a storage pit. Also in this case, it is identified as a surge pit. From the storage pit, the waste are pushed onto a conveyor system to be transported to the shredder. After shredding, ferrous metal is removed and the waste are compacted into the transfer trailers for transport to the disposal site. Now let me talk about the transport means and methods. Motor vehicles, railroads, and ocean-going vessels are the principal means now used to transport solid wastes. Pneumatic and hydraulic systems have also been used. Where the point of final disposition can be reached by motor vehicles, the most common means used to transport solid waste from transfer stations are trailers, semi-trailers, and compactors. All types of vehicles can be used in conjunction with other type of transfer station. In general, vehicles used for hauling on highways should satisfy the following requirements. Waste must be transported at minimum cost. Waste must be covered during the whole operation. Vehicles must be designed for highway traffic. Vehicle capacity must be such that the allowable weight limits are not exceeded, and methods used for unloading must be simple and dependable. This slide represents the locations of the transfer stations and landfills in Istanbul province on this map. In total, there are 8 transfer stations in Istanbul. 4 of them are in Anatolian side and 4 of them are in European side. The transfer stations in Anatolian side are in Tuzla Aydınlı, Ümraniye Hekimbaşı, Küçükbakkalköy, and in Şile. The stations in European side are in Baruthane, Yenibosna, Halkalı, and in Silivri. There are two active municipal solid waste landfills. The one in Anatolian side is Kömürcüoda landfill, and the other one in European side is in Silivri. The landfill in Odayeri was closed after about 25-year operation after the construction of the new airport close to it last year. These are the photographs taken from one of the direct load transfer stations with compaction in Istanbul. The collection vehicles are in the upper platform and unloading the municipal solid waste that they were collected from the residential areas to the container of the transport trailer in the lower platform. After the municipal solid waste is unloaded, a compactor, as the one that you see on the right, is used for the compaction of the waste in the transport trailer. In the slide, you see the photographs of transport vehicles taken in one of the direct load transfer stations in Istanbul and in the landfill when they are unloading the municipal solid waste. Is a transfer station appropriate for your community? This is one of the crucial questions that the local authorities are looking for, and the answer can only be given by comparing the costs and savings associated with the construction and operation of the transfer station. By the way, the benefits and possible drawbacks should also be considered. What are the expected benefits? Lower collection costs, reduced fuel and maintenance costs for collection vehicles, increased flexibility in selecting disposal facilities, the option to separate and recover recyclables or compostables at the transfer site, the opportunity to shred or bale wastes before disposal. What about the possible drawbacks? Difficulty with sitting and permitting, particularly in urban areas, and construction and operation costs may make them undesirable for some communities. Although specific details vary with size, important factors that must be considered in the design of transfer stations include the type of transfer operation to be used, storage and throughput capacity requirements, equipment and accessory requirements, and sanitation requirements. From a design standpoint, the key issue is whether waste recovery operations will be incorporated into the transfer station facility. If waste recovery is to be accomplished at the transfer station, then an adequate area must be available for the collection vehicles to unload. Both the throughput and storage capacity requirements must be evaluated carefully in planning and designing transfer facilities. The throughput capacity of a transfer station must be such that the collection vehicles do not have to wait too long to unload. In most cases, it will not be cost-effective to design the station to handle the ultimate peak number of hourly loads. Ideally, an economic trade-off analysis should be made. For example, for both types of transfer stations, the annual cost of the time spent by collection vehicles waiting to unload must be traded off against the incremental annual cost of a transfer station and/or the use of more transport equipment. Because of the increased cost of transport equipment, a trade-off analysis must also be made between the capacity of the transfer station and the cost of the transport operation, including both equipment and labor components. For instance, in a given situation, it may be more cost-effective to increase the capacity of a transfer station and to operate with fewer transport vehicles by increasing the working hours than to use a smaller transfer station and purchase more transport vehicles. In a storage load transfer station, the equivalent storage capacity varies from 1/2 to 1 day's volume of waste. The capacity also varies with the type of auxiliary equipment used to load the transport vehicles. Seldom will the nominal storage capacity exceed 3 days' volume of waste. The equipment and accessories used in conjunction with a transfer station depend on the function of the transfer station in the waste management system. In a direct load transfer station, some sort of rig, usually rubber-tired, is required to push the waste into the transfer vehicles. Another rig is required to push the waste and to equalize the load in the transfer vehicles. The types and amounts of equipment required vary with the capacity of the station. In a pit-type storage load transfer station, one or more tractors are required to break up the waste and to push them into the loading hopper. Additional equipment is required to distribute the waste and to equalize the loads. In some installations, an overhead crane has been used successfully for both purposes. Scales should be provided at all medium and large-size transfer stations, both to monitor the operation and to develop meaningful management and engineering data. Scales are also necessary when the transfer station is to be used by the public and the charts are to be based on weight. If scales are to be used, it will usually be necessary to provide an enclosure for them. The scale house, as it is commonly called, should also have an office equipped with a telephone and a two-way speaker system so that the weight masters can talk with the drivers. If the transfer station is to be used as a dispatch center or district headquarters for a solid waste collection operation, a more complete facility should be constructed. For a headquarters facility, a lunchroom, meetings room, offices, locker rooms, showers and toilets should be provided. Facilities for providing equipment maintenance may also be incorporated. By proper construction and operation, the objectionable features of transfer stations can be minimized. Most of the modern, large transfer stations are enclosed and are constructed of materials that can be maintained and cleaned easily. To eliminate emissions, enclosed facilities should have air handling equipment that creates a negative pressure within the facility. In most cases, fireproof construction is used for direct load transfer stations with open loading areas. Special attention must be given to the problem of blowing papers. Windscreens or other barriers are commonly used. Regardless of the type of station, the design and construction should be such that all areas where rubbish or paper can accumulate are eliminated. The best way to maintain overall sanitation of a transfer station is to monitor the operation continually. Spilled solid waste should be picked up immediately or in any case should not be allowed to accumulate for more than 1 or 2 hours. The area should also be washed down. In some large facilities, wastewater pre-treatment facilities may be required to treat plant wastewater before it is discharged to the local sewer. In remote areas, complete wastewater treatment facilities may be required. Health and safety issues at transfer stations are related to dust inhalation and other requirements. Overhead water sprays are used to keep the dust down in the storage area of a storage load transfer station. To prevent dust inhalation, workers should wear dust masks. In storage load transfer stations, tractors in the pit area should have enclosed cabs equipped with air conditioning and dust filtering units. For reasons of safety, the public should not be allowed to discharge waste directly in the storage pit at large storage load transfer stations. Whenever possible, transfer stations should be located as near as possible to the weight center of the individual solid waste production areas to be served, within easy access of major arterial highway routes as well as near secondary or supplemental means of transportation, where there will be a minimum of public and environmental objection to the transfer stations, and where construction and operation will be most economical. Additionally, if the transfer station site is to be used for processing operations involving materials recovery and/or energy production, the requirements for those operations must also be assessed. In some cases, these latter requirements may be controlling. Under ideal conditions, the transfer stations should be located so as to minimize transportation costs. However, given the difficulty most waste management agencies have had in recent times in locating transfer stations, transportation costs have become somewhat less important in the selection of an appropriate location of a transfer station. Hereafter, I will talk about the solution of 3 examples about transfer and transport operations from our textbook. The first example is about the economic comparison of transport alternatives. The question asks to determine, based on operating cost, the break-even points for a hold and a stationary container system as compared with a system using transfer and transport operations for transporting waste collected from a metropolitan area to landfill disposal site. The following operating cost data are applicable. Hold container system using a hoist truck with a 6 meter cube container is $25 per hour. Stationary container system using a 15 meter cube compactor is $40 per hour. Tractor unit with a capacity of 80 meter cube is $40 per hour. Transfer station operating cost is $3.6 per meter cube. Here is the solution of this example. First of all, let's convert the whole cost data to units of dollars per cubic meter per minute. For hoist truck, it is calculated by dividing the whole cost data of hoist truck, which is $25 per hour, to 6 meter cube, which is the capacity of the whole container. And this value is converted to minute by dividing by 60 minutes per hour. And the result is $0.0694 per meter cube per minute. And for the collection vehicle with compactor, it is calculated by dividing the whole cost data of collection vehicle with compactor, which is $40 per hour, by 15 meter cube, which is the capacity of this vehicle. And this value is converted to minute by dividing by 60 minutes per hour. And the result is $0.0444 per meter cube per minute. Finally, the same calculation is done for transport truck. And this calculation is done by dividing the $40 per hour, which is the whole cost data of transport truck, to 80 meter cube, which is the capacity of this vehicle. And the calculated data is converted to minute by dividing that data to 60 minutes per hour. And the result is 0.0083 meter cube per minute. And now let's prepare a plot of the cost per cubic meter versus the round-up driving time expressed in minutes for the 3 alternatives using the values calculated above. The required plot is presented in the next slide. Before plotting the graph of per cubic meter versus the round-trip driving time, firstly, let's prepare such a table that you see in the left-hand side of the slide. In this table, the first column is the time in minutes, and it increases by 10 minutes from 0 to 110. The second, third, and the last columns are the costs of hold container system, stationary container system, and transfer station operations in dollar per meter cube. Let me explain how these cost values are calculated. For the 10-minute round-trip driving time to disposal site, the cost of hold container system is 10 minutes times unit cost of hold container system, which is $0.0694 per meter cube per minute. It makes $0.694 per meter cube. The cost of stationary container system is calculated by 10 minutes times $0.0444 per meter cube per minute, the unit cost of stationary container system, and it makes $0.444 per meter cube. The cost of transfer station operation is calculated by multiplying the round-trip driving time of 10 minutes with $0.0083 per meter cube per minute, which is the unit cost of the transport vehicle. And the result is summed up with the cost of transfer station operation, which is given in the question as $3.6 per meter cube. The calculations are repeated till 110 minutes round-trip driving time to disposal site, and finally the table is ready. By using this table, the graph on the right is plotted. In the graph, the projection of the point where the green and red lines intersect gives the break-even time for whole container system, which is 59 minutes. The projection of the point where the green and blue lines intersect gives the break-even time for stationary container system, which is 100 minutes. As a result, if a stationary container system is used and the round-trip driving time to the disposal site is more than 100 minutes, the use of a transfer station should be investigated. If a whole container system is used and the round-trip driving time to the disposal site is more than 59 minutes, the use of a transfer station should be investigated. In most cases, reference books dealing with the long-distance hauling of solid waste, cost data are expressed in terms of dollars per ton per minute. This practice is widely accepted for transfer station analysis because weight is the most critical measure for efficient highway or rail movement. Such cost data can be misleading. However, when the densities of solid waste vary significantly from location to location or container to container. For example, if the density of the wastes in 2 hoist truck containers varies by a factor of 3, then comparing the costs of hauling 2 containers of the same size on a per ton basis would tend to be misleading because the actual cost is the same for both. On the other hand, a comparison based on dollars per cubic meter per minute or dollars per minute would be valuable in comparing the two operations. Now let me solve a problem and show you how to determine the break-even times for a transfer and transport system using the cost data expressed in terms of dollars per ton per minute. In this problem, you are asked to determine the break-even times for the two container systems versus the use of a transfer and transport system. The computations have to be based on dollar per ton per minute. Assume that the following cost data are applicable. There are two stationary container systems. The first one uses 4-ton capacity collection vehicles, and the second one uses 10-ton capacity collection vehicles. The operating costs of the 4-ton capacity vehicle-based stationary container system is $25 per hour, and the operating cost of the 10-ton capacity vehicle-based stationary container system is $36 per hour. For transportation of the municipal solid waste to the landfill, a 25-ton capacity truck semi-trailer is used, and its cost is $55 per hour. And finally, the operating cost of transfer station is assumed to be $3 per ton of municipal solid waste. Here is the solution of this problem. First of all, let's convert the whole cost data in dollar per hour to dollar per ton per minute. The whole cost of 4-ton capacity vehicle-based stationary container system is $25 per hour divided by 4 tons and divided by 1 hour over 60 minutes, and it is equal to $0.104 per ton per minute. The direct whole cost of 10-ton capacity vehicle-based stationary container system is $36 per hour divided by 10 tons divided by 1 hour over 60 minutes, and it is equal to $0.060 per ton per minute. The transport cost of truck semi-trailer is $55 per hour divided by 25 tons divided by 1 hour over 60 minutes, and it is equal to $0.0367 per ton per minute. The transport truck semi-trailer is used in combination with the transfer station. So the baseline cost of this combination, which is at round trip time 0, is $3 per ton. To determine the cost per ton for each system based on the round-trip driving time in minutes, firstly, let's set up a computation table and then plot an XY graph. Before plotting the graph of dollar per ton versus the round-trip driving time in minutes, firstly, the computation table that you see in the left-hand side of the slide is prepared. In this table, the first column represents the round-trip driving time in minutes, and the values in this column are in between 0 and 200 minutes at 20-minute intervals. The second, third, and the last columns represent the cost of 4 and 10-ton capacity collection vehicles and the transfer station operation plus truck semi-trailer in dollar per ton. Let me explain how the values in the second row, which is 20-minute round-trip driving time are calculated. For 4-ton capacity collection vehicle, it is 20 minutes times $0.0104 per ton per minute. It is the unit cost of 4-ton capacity vehicle and it makes $2.08 per ton. For the 10-ton capacity collection vehicle, it is 20 minutes times $0.060 per ton per minute. It is the unit cost of 10-ton capacity vehicle and it makes $1.2 per ton. The cost of the transfer station operation is calculated by multiplying the round-trip driving time of 20 minutes with $0.00367 per ton per minute, which is the unit cost of the transport vehicle. And the results of this multiplication is added onto the cost of the transfer station operation, which is given in the question as $3 per ton. Same calculations are repeated up to 200 minutes of round-trip driving time to the disposal site. And finally, the computation table is ready to plot the graph. And by using this table, the graph that you see on the right is plotted. In the graph, the projection of the point where the green and red lines intersect gives the break-even time for the 4-ton capacity vehicle based stationary container system, and it is about 45 minutes. The projection of the point where the green and blue lines intersect gives the break-even time for the 10-ton capacity vehicle based stationary container system, and it is about 130 minutes. As a result, if 10-ton capacity collection vehicles are used and the round-trip driving time to the disposal site is more than 45 minutes, the use of a transfer station should be investigated. If 10-ton capacity collection vehicles are used and the round-trip driving time to the disposal site is more than 130 minutes, the use of a transfer station should be investigated. This is the last problem that I will solve in this lecture. In this problem, you are asked to estimate the peak hourly capacity of the transfer station shown here on the slide in number of vehicles per hour and ton per hour. This transfer station is a large capacity direct load transfer station without compaction, which was constructed in a two-level arrangement. Upon arrival at transfer station, all collection vehicles hauling waste are weighed on the platform scale. Then the collection vehicles climb up to the elevated unloading platform through the approach ramp. And then there they empty their contents directly into the transport trailers on the lower platform positioned under loading hopper. In the problem, the average volume per vehicle and the specific weight of the waste are given as 12 meter cube and 280 kg per meter cube respectively. Any other assumptions made in solving this problem should be stated. This is the solution of the problem 10.5. Let's start with stating the assumptions made. This transfer station is a direct load station. Therefore, municipal solid waste will not be stored on the platform. In the elevated unloading platform, 6 collection vehicles can unload at the same time, one per trailer hopper. The total time required to get a collection vehicle unloaded, including the time spent driving onto the unloading platform, unloading and driving off the unloading platform, and the time needed to clear the platform between the collection vehicles is 10 minutes. The maximum number of collection vehicles that can be handled per hour is calculated by dividing 60 minutes per hour by 10 minutes per cycle, which is the third assumption, and 6 trucks per cycle, which is the second assumption. It is computed as 36 collection vehicles per hour. The peak capacity of the transfer station, expressed in ton per hour, is estimated by multiplying the maximum number of vehicles per hour, which is 36 by 12 meter cube per hour, which is the average volume of the collection vehicle, and 280 kg per meter cube, which is the specific weight of the solid waste. And the result is divided by 1000 to convert it to ton per hour. The result is 121 tons per hour.